Hi. I don't know if I mentioned before, but section 8.2 is extremely important. We are going to be doing hypothesis testing for the rest of the semester. So once you get hypothesis testing down, then the rest of the semester is going to go much easier. Now, this section does have a lot of stuff in it. It does have a lot of parts to it, some new language. The way that I taught chapters 6 and 7 was leading up to hypothesis testing. So there was a lot of stuff we did in chapters 6 and 7 that we're going to do again here. So this is going to be a bit of a long recording. You may want to put it on pause and go get some tea at some point or whatever, but be sure to come back. It's really good stuff. All right, here we go. Oh, one other thing is for the rest of the semester, it's basically going to be 8.3. Here's one little new idea. Now we do hypothesis testing. 8.4. Here's one little new idea. Here's hypothesis testing. So if you don't get it right away, or you don't remember everything from section 8.2, it's going to be gone over again and again throughout this section. So eventually you will get it. Here's the overall idea. Somebody makes some kind of claim, like that adults average 8 hours of sleep a night. And then you want to prove them wrong. So you get a sample, random sample of course, and you find out that the average is much lower. It's 7.2 with S equal to 1.2. So the main question is this sample data from 40 people, is this enough to prove that claim of 8 hours wrong? Or is it just not enough data? Do you need 400 people instead of 40? So that's the main idea. But hypothesis tests are set up in a very structured way, which has its good points and its bad points. The bad point would be you have to do it the way they say. The good point is it's going to be the same every time. It's going to be once you get it set up, it's set up that way and that way again and again. So that's what we need to work on. What do we do first? Write down the claim. Since this is a math class, the claims are going to have numbers. That means that there can be one of 6 symbols. They could say less than or equal, bigger, bigger than or equal, etc. Well, the next thing you do is you write down what's called the alternate hypothesis. So this basically says, you know what? Why do we have to have 6 cases? Can't we just narrow it down to 3 cases? And the 3 cases that it narrows it down to are those that have less than, bigger than, or not equals. Okay, now for the easiest one, the null hypothesis, called H sub O. For this one, it has equals no matter what. It doesn't pay attention to what anybody else says, it's just going to have equals. An important note about the alternate hypothesis. So, if the claim has a less than, or a bigger than, or not equals, then H1, well, it just uses one of those symbols, whatever it is. So H1 would be the same as the claim. If the claim has a less than or equal, bigger than or equal, or an equals in it, then you have to use the opposite. So these two guys, equals and not equals, are opposite of each other. For this one, bigger than or equal, you have to use the opposite direction, and it can't have an equals. So the opposite of this one would be this one. Likewise, the opposite of less than or equal is going to be greater than. Okay, so now let's practice setting those things up. So it could be a claim about a mean, like the mean is at least 42, and at least means bigger than or equal. So the mean would be mu, at least is bigger than. H1 can't have an equals in it, so it uses the opposite, less than. And here's H sub O with its equals. Next, it could be about a proportion, so let's say that it's over 80%. So we use P for proportion and 0.80 for 80%. And then, of course, over would be this way, bigger than. And then H1 would say, hey, I can use that symbol, so it just stays the same. And then, like always, H sub O says, I'm ignoring you guys, I'm just going to say equals. Could also be a claim about the standard deviation. So let's say standard deviation equals 15. And in this case, H1 can't have an equals, so it has the not equals. All right. The next thing to do is draw the bell-shaped curve and find the critical values. Well, you may remember we did this in Chapter 7. We used Table A2, Table A3, and Table A4. Which table do we use when? Well, if it's something about proportions, like that last one said something about 80%, one of them said something about 80%. If it's about proportions, you always use Z. There's no choice. You use Table A2. If it's a claim about standard deviations, there is, again, no choice. You have to use chi-squared or Table A4. The only one that has a choice is when it's a claim about a mean. There's two possibilities. The sigma is known, so that means you know the standard deviation for the whole population. If that's true, then you can use the Z distribution or Table A2. If the sigma is not known, that means you only know the S, the lowercase s for standard deviation for a sample. Well, in that case, you use the T distribution, Table A3. Now, this question comes up because when we made confidence intervals had a left side and a right side, so there were two critical values, always. With hypothesis testing, that's not always true, but don't worry. If you wrote down the H1, it will tell you exactly what to do. That's part of the beauty of that structure, is once you have it down, it basically guides you through it. So if the H1 has a bigger than, and I'm not even paying attention to the numbers, I'm just looking at this symbol. If this is pointing to the right, it's a right-tailed test. So the picture you draw would look like this. And if we were using, let's say, 98% level of confidence, then alpha equals 0.02, the whole thing would go right here, 0.02. And then we would look up the critical value, Table A2. We'll practice that in just a second. If the little arrow is pointing to the left, then it's going to be a left-tailed test. So the picture would look like this. The critical value being on the left is now negative. And then if it says that P is not equals, then that means it's a two-tailed test. So up here I said if alpha equals 0.02. Well, if that's the case, then in this one you'd have to take that 2%, put 0.01 here and 0.01 here. And then you would have two critical values. So, as an example, find the critical value using 98% level of confidence. The claim is the proportion is at least 50%. So this is going to be P. At least means bigger than or equal. This is going to be 0.50. So the P is at least 0.50. H1 has to have the opposite of bigger than or equal. So it points to the left, left tail. There's H sub O. And since we're using 98% level of confidence, then this is 0.02. Next, I would draw the picture and say this is 0.02 in this tail. Since it's on the left, the critical value is going to be negative. And then we get table A2. And since this equals 0.02, we then look through the table to what's closest to 0.02, and it's right here, where it says 0.0202. So that is going to be, if you look to the left, negative 2.05. So the critical value, negative 2.05. All right, so now let's do a full example with all these pieces put together. Test the claim that 50% of people feel they are optimistic. Out of 130 interviewed, 68 said they were optimistic. And we're going to use the 95% level of confidence. So first, I would write down the claim, which has equals, because it says test the claim that 50% of the people. H1 can't have an equals, so it's not equals. That makes it a two-tailed test. H sub O always just has its equals. And using 95% level of confidence means that the alpha is equal to 0.05. So next, draw the picture. Since it's two tails, we're going to have to take this 5% and cut it in half. 2.5% on this side, 2.5% on this side. Next, I would write down the sample data. So out of 130 people, there were 68 that said they were optimistic. You divide those two, and you find out that the sample percentage is 52.3%. Now the idea is, somebody said it's going to be exactly 50%. And then you can say, aha, no it's not. It's over 52%. You're so wrong. But is 52% really that different from 50% that you can say these people were wrong? Well, that's where we're headed. Let's find out. So we need to look up those critical values. So looking for 0.025. 0.025. There it is. I found it. So if you look to the left, it's going to be negative 1.9 and 6. Goodbye, table. Hello, critical values. Negative 1.96, and then on the other side, positive 1.96. Now we do the z-score. We've done the z-score for many chapters. With hypothesis testing, it gets a nice formal name. It's called the test statistic. Sounds very formal. So that's what we're going to be calling the z-score, the t-score. Those guys are going to be called the test statistic from now on. So this is the z-score, where we've got the p hat minus the number that was in the claim. Then this is p hat, and this is q hat, which you may remember is 1 minus p hat. And then this is the n. So put all of that in a calculator. This is what you get, 0.525. I'm going over this sort of fast because, as I mentioned before, I'll do the formulas once so that you see what is involved, but then we're going to be using the calculator for this part, and you don't have to use the formula. So the next idea is this critical value is saying, well, somebody said that it's 50%, but is this data really that unusual? Is it almost 2 standard deviations away from average? Well, this over here is saying no, it's only half a standard deviation away. So this would land right about here, which means that it's only half a standard deviation away, which is not that unusual. So what they said does not stand out as unusual. This contradicts it a little bit, but is it strong enough to say they were wrong? No. So consequently, we were not able to prove anything. And this is the formal way that it said, failed to reject. The more informal way is we are not able to prove anything. Okay, so now, what can the calculator do? So start by going to stat and then tests. And we've been using the confidence interval part before, but look at number 1 through 7. That right there is chapter 8 and chapter 9, hypothesis testing. So all of these formulas, you don't have to remember them. And in fact, you can use this little screen right here to help you, because you can say, okay, now it's a test. Which one is it? Which one is it? Oh, it's about proportions. That's right. It even said proportion in the problem. Okay, yeah, I use this. And did I have one group or did I have 2 groups? No, there's just optimistic people, so I only had 1 group. Okay, it's number 5 right here. So you would choose that. Then you just need to type in this right here is saying, if you were to look at H sub O, what is the percentage? So 0.50. So these are the successes out of the sample size, and then put calculate. So it will tell you the z value, 526. I don't remember getting a 526. I got a 523 or something like that. Well, the thing is, the calculator is more accurate, because when I use this as the p hat, the calculator actually uses that out to, I think it's 12 decimal places in its calculation. So it uses 12 decimal places in its calculation. So actually this is more accurate than what I had on the previous screen. So anyway, this is not enough to go past 1.96, so it's going to be failed to reject. Another thing that it gives you is what's called the p-value. So that's this. This p-value means basically this has to be a very small percent in order to reject. It basically needs to be smaller than the 5% that we had as our alpha. Since it's not small, then you cannot reject. In a way, it's saying if you reject them, there's a 59.9% chance you're wrong. So don't reject them. All right, for the last part of it, how do those conclusions work? So let's say that this is what the picture looks like. It doesn't have to be two-tailed, but it's got to have at least one tail, and that's really where the story is. So let's say that the test statistic lands over here, or over there. Doesn't matter. But it definitely goes past a critical value, or in other words, it lands in the shaded area, or in other words, it lands in the critical region, it's called. So if that happens, then we actually just prove something. So you would start by saying reject H sub O. And what we're really saying is whoever said they're equal, they're wrong. They're not equal because this is unusual. And if something unusual happened, it's because whoever made up the claim, they were not right. This 50% that they made up is wrong. All right? Then the other possibility is it lands somewhere in the middle. So somewhere, it could land right here, right here, right here, right here, right here, but it doesn't go into the shaded part. Then you did not prove anything. Either that's because you don't have enough data, in other words, interviewing 40 people was not enough, you should have interviewed 400 people, or somebody says it's 50% and your data says it's 51%, well, those two are too close. You can't contradict their 50% when you say it's 51%. So that would be called failed to reject. Or in other words, in English, it would be we are not able to prove anything. All right, so I know this section was sort of long, but like I said, we're going to be doing it over and over again. So the faster you get it down, the easier the rest of the semester is going to be. So see you in the next section, 8.3. Bye.